Okay, today we got into the Middle Fork River. This was day one, and we focused on doing transects, and we are calculating the stream flow of the Middle Fork River. So here's a visual, and here's what we did today. We had one group take a walk along this path here, and they entered here, and they were along this riffle system. And the riffle were simply just a bunch of rocks at the bottom of the Middle Fork River. And we had another group kind of take an adventurous path. They walked across the bridge, and they kind of had to navigate their way to this location. Here was a set of riffles. And we had another group come over here, walk down this path, and they got in, and their entry point was over here. So we had three different locations, three different riffle systems that we got into. And we did a transect. We pulled a tape measure apart. Trans means across, so we're going across the river along the riffle system. And we will eventually be moving into the pool. It's a little bit deeper. It'll have different characteristics. We'll talk about that later. But today we just got started with stream flow. And when we talk about what stream flow is, we're talking about it's a measurement. It's a quantity where we measure the width, and we multiply that times the depth, right? These are averages. We get multiple data pieces. And we multiply that times the velocity. And at the end, the stream flow measurement is a volumetric measure measured in cubic meters that are traveling each second. So it's technically called volumetric flow. So today we focused on the riffle. And in here, what we will be able to see and observe when we stand on the bridge and we look either direction, whether we look upstream or look downstream, we will actually see that the dynamics of a riffle are going to be different than that of the pool. And we'll get into this here in just a few minutes when we look at this mathematically. We'll look at why. But a riffle, in general, you can actually see the water moving. It's relatively shallow, and it's traveling relatively fast velocity. But the pool is going to be deeper, and it's going to be traveling really, really slow. And we'll come to this. Well, I'll come back to this, and I'll end on this. So now let's look at our data. And I took data points from students in class. So I took data, your own data, and I'll just call this Lab Station X. Here's a similar version of the handout you got today that's not identical. It should be close. So we took a tape measure, and the tape measure was how we measured how wide it was. So I just took an average of class data. So it was roughly on average, it was 8.1 meters across. So this transect was the width of the Middle Fork River, right? The transect. And let's say 8.1 meters. So here we go, sorry. And then along each 1 meter increment along here, right? So here would be 1 meter, here would be 1 meter, here would be 1 meter, and whichever side you start on, I'm not that concerned about. But we take a measurement each 1 meter increment. So 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 meters wide, right? 8.1. We'll go with 8 meters here. Just kind of makes it a more round number. We're going to be close. 10 centimeters. We'll have some error here, and that's okay. So that means we measured at 1 meter away from the shoreline, right? We're essentially measuring from side to side. So if I look at this as like a picture, we're measuring across here. We know the width. And if this is where we start, 1 meter away, we would say that it was 8 centimeters. And then another meter away, it was 13 centimeters. And another meter away was 19. Right, it kind of got a little bit deeper, according to my data here. And then it was 22, and then it starts getting shallower, and then it gets a little bit shallower and less shallow, and then all of a sudden you come to your shoreline. So these are measurements at 1 meter interval. These are the depths. So if I add up these numbers, I get a total of 96. But when I find my average depth, I can't ignore that the shoreline is 0 here and the shoreline is 0 here. So I have to add these into my divider, my denominator. So I have to divide it by 10 data points. So 10 data points includes the 0 that I start from and the 0 that I end with, and those are the shorelines. So it's essentially the geometry of this transect for the cross-sectional area. So I came up with 9.6 centimeter average. I need to convert centimeters. Centimeters has to be converted into meters. And if there's 100 centimeters in 1 meter, I take 9.6 centimeters divided by 100, and I get 0.096 meters. And we'll come back to this data here. And then I took times from students in class data. What was the velocity, right? That's what we're looking for. What is the velocity in meters per second? So let's say it took 5.5 seconds to travel 1 meter, it took 7.6 seconds to travel 1 meter, it took 4.6 seconds to travel 1 meter. And these all come with some range of error. We're doing this manually, but I just want you to see how it goes about doing it. There's a lot of technology pieces that allow us to do this, but we're doing it manually. So I can solve the velocity is going to be distance divided by time. I take 1 meter divided by the time here of 5.5 seconds, and this velocity is 0.18 meters per second. I do the same thing. I'll zoom in a little bit. I take 1 meter, right, velocity distance divided by time, 1 meter divided by 7.4 seconds, I get 0.14 meters per second, and I take 1 meter divided by 4.6 seconds, and I get 0.22 meters per second. And so I document them in my final column, and I get an average of 0.18 meters per second for my velocity. So now I have my data. And this is where we start putting it all together, and I want you to see this. I think this is the important stuff, because once you collect the data, now you need to do something with it, and this is what we're doing. My width average, I'm going to go ahead and say, was 8.1 meters, and my depth average was 0.096 meters. Right? It wasn't very deep. Right? That's not very deep. That's actually quite shallow. So that's about 10 centimeters, right? 10 centimeters is roughly, I don't know, size of your pinky, a little longer than your pinky, maybe one of your fingers. We all have different size fingers, so that's a tricky one. And multiply this times my velocity average, which I get over here, which was 0.18 meters per second. And so now I'm going to quantify this. I take 8.1 times 0.096 times 0.18. And you'll find it's a tiny, tiny amount here, right? My value, when I multiply these, go ahead and put it right here, I get my stream flow is 0.14 cubic meters per second, right? That's how much volumetric flow is traveling. It's not that much. The Middle Fork River is a tiny, tiny little river, a tiny tributary of other rivers. So here's my calculation here. 0.14 cubic meters traveling per second. Now, this is stream flow. So this would be, according to my transect, along the riffle, right? That's all we did. We just simply did it along the riffle, right? Up here in my directions, the riffle only. The cross section, and this is where I use my data here to make sense of what's going on here. So now we're going to draw a cross-sectional profile of what took place here. So let's do this. So I know that at 0 was the shoreline, right? Zero shore was my shoreline. That's where the water meets the shore. Well, 1 meter out, according to my data, says it was about 8 centimeters in depth. So I'm simply saying at 1 meter width, 1 meter from the shoreline, it's 8 centimeters in depth. That's close enough. It's pretty close here. My 2 meter mark was 13 centimeters. My 3 meter mark was 19 centimeters. Right, so I'm simply aligning them this way. My 4 meter mark, so 1, 2, 3, 4. Sorry, I'm losing it. Getting a little sidetracked here. Right here. Okay, simply just cross-referencing my x and y coordinates. The next, notice it gets shallower. Boom! Look at this. It's only 14. So 14 here. And the next one was 11 over here. Notice you have extra boxes. It's simply that's different. There's different depths, right? There's different widths are going to determine that there'll be different depths. But here, I don't have to use all these data pieces. I'm only measuring 1 meter increments, so I'm consistent with my data points. So 6 meters is 11. 6 meters is 11. And 7 measure was 7. And the 8, which I'm pretty much just saying 8, was my other shoreline. So notice, here's the contours. And this is dramatically exaggerated to the vertical scale. But that's okay. That's okay. Here's the channel of the water. This is what it looked like based on my data. So here's where we find the water. Notice, sometimes they can be kind of funky looking because there are rocks in here. That's what the riffles do. So notice, this water was moving. So this cross-sectional area, traveling at this velocity, right here, has this much volume of flow traveling. And what's going to happen here is this. Now we're going to start making sense as to, well, this is just for the riffle. And once again, this is exaggerated. You'll find that the pool that we have not yet gotten into, the riffle is going to be shallow and traveling fast. And the pool is going to be deep and traveling slow. And now we need to look at, well, let's just say what's going on. How does that happen? So now we need to look at what's happening with streamflow. Because if you can imagine the Middle Fork River just in the pictorial representation, and I'm only going to focus on one of these. So let's say I have this riffle here, and I have a pool here. Right? So here's the pool, and here's the riffle. This water here, the total amount of stream flow at this location along my riffle must be exactly the same of the stream flow along the pool, right? This is going to equal this, but they have different contours, and this is where we can look at this. So let's look at this algebraically first. That the stream flow of the riffle is going to be width times depth times velocity, and the stream flow of the pool is going to be the width times the depth times the velocity. But you'll find that the widths are going to pretty much be the same. They're going to be identical, right? That's about the same width. There's not that dramatic of a difference here. What you're going to find different is this, that the stream flow for the riffle is going to equal the stream flow for the pool. And here's why. Because the depth times the velocity of the riffle is going to equal the depth times the velocity of the pool. In other words, it's a lot shallower here. Therefore, in order to compensate for total stream flow, it must be traveling faster. Whereas in the pool, it's going to be much, much deeper, and therefore to keep stream flow constant, it's going to be traveling at a slower velocity. So when we look at what's taking place here, conceptually, the riffle is going to be shallower. It has to travel faster, right? That's simply a dynamic of stream flow. And where it's deep in the pool system, it's going to be traveling slower. So when you stand on the bridge here, you can look and you can actually see where you see water moving, where you can actually visually see it. You must be looking at a location that's traveling fast. And if it's traveling fast, it must be shallower. And where you cannot see it moving, it almost looks like it's static, is where you're going to be seeing within the pools, because it's traveling so slow. And that's all calculated by knowing that the stream flow at the riffle with depth velocity is going to equal the stream flow at the pool with depth velocity. The only thing different, right, noticeably different, right, the widths are going to be about the same, is that where you have shallower depths, it's going to compensate by traveling faster. I hope that helps.